Okay, so off we go, picking up where we were last time. So we finished 5.2 on to 5.3. We're going to cover 5.3 in about 5 minutes. It's a very short section. There's really only one big idea. I am not clear why this isn't just part of 5.2, frankly. It's not that much to it. So here's the big idea. When you have an iterated integral, if that iterated integral is hard to compute, try slicing it in the other direction. That's the big idea here. Now, if it comes to you initially as an iterated integral and you don't know what the original double integral is, the point is you can kind of reverse engineer, find the original double integral, and then literally just slice it the other direction. So here we go. Let's first recognize what is hard about this iterated integral given to us. And what's hard about it is if you look at the inside integral, this inside integral requires knowing that antiderivative, and you can't do it, loosely speaking. If you use the power series, then you can. But in regular old normal terms, what we call closed form, there is no antiderivative of this function. So that's a problem. I can't work it out if that's the case. So we're going to then reverse engineer and figure out what was the original double integral. What is the original domain that we're actually dealing with here? So, well, keep in mind these bounds here, right, on y going from 0 to 1, what that tells me is that my domain is in between those lines, y equals 0 and y equals 1. Right there. And then furthermore, this inside inner bound, lower bound, x equals y, that tells me that that's one of my bounds, literally the equation x equals y, and then this other one, x equals 1, is another one of the bounds. So putting it all together then, my domain, y goes from 0 to 1, and then for any given value of y, we go from green to purple. And altogether then, I think it's pretty clear what our domain is. Our domain is this shaded region right there that I was trying to turn yellow. There you go. There's your original domain. So now, are we going to compute this double integral now, knowing our domain as we do? Are we going to compute this double integral directly or something? Well, no, of course not. We're just going to slice the other way. And now this is a pretty straightforward domain. Looking at this domain, again, here it's this triangular region. Not much to it. And if you slice that with x on the outside, then you see x goes from 0 to 1. Right? And then for a given value of x, looking at that x slice, y starts at y equals 0, and y ends on that curve where y equals x. So what we've done, now just as we originally said, we took an iterated integral, we reverse engineered the domain, viewing it as a double integral, and then we sliced the other direction to now get a brand new iterated integral. Now the very first thing you're going to look at, you see in here, this iterated integral we're looking at, it seems to have the same problem as the first one, namely our integrand is e to the x squared. And didn't we just get through saying that you can't integrate that? Well, conveniently, at this point, we need to find its integral with respect to y. And x, you will notice, is further to the outside, which means for that y integral, not only is x a constant, but e to the x squared is just a great big constant. And this is a really easy integral. The y antiderivative would just be y times e to the x squared, and then you plug in the bounds, and you get, why don't I just do it like this? You get that. So in this case, the point is, changing the order of integration turns a really hard integral into a really easy integral. And the outside integral at this point now, looking at this x integral, this being our integrand, there's a really easy u substitution. which I think I have. Yeah, here we go. Just plug in u equals x squared, and everything just works out just fine. So, nice little trick. That's all there is to it. That's the substantial part of section 5.3. And so I'm going to declare us done with 5.3, and we're going to move on to 5.4 now, triple integrals. So this is a very substantial discussion. There's a lot going on with triple integrals. First, the good news. The good news is that triple integrals are really a lot like double integrals. Pretty much the same ideas, just three-dimensional instead of two. So since it is so similar in so many ways, I am going to hustle through the definition and the development and the connection between all the stuff that we went through very carefully and very slowly with double integrals. I'm going to mostly say, same story, right? Here's the bad news. The bad news is triple integrals, no surprise, the word triple, we are talking about three-dimensional regions now, and so the pictures we're going to draw are going to be harder pictures. They are unavoidably three-dimensional pictures. There's just no way around that, right? So we're going to have to, therefore, do a bunch of examples because the geometry gets very confusing. Now, what's the best way to deal with complicated geometry? I am a devout believer in the pictures. You've got to be able to draw a good picture. You're going to hear me say that several times today. Look at the picture. It's very important to see the picture, stuff like that. If you are not good at drawing three-dimensional pictures, that's something we need to address. That's something that has to be improved. There is no algebraic sort of workaround that avoids having to be able to draw good pictures. So I'm going to make a reference now. So I've had 1 million students ask me over the years, how do I get better at drawing three-dimensional pictures? And rather than explain it, over and over and over again, same ideas, I put them into some videos. So it's easily accessible on the YouTube channel. The playlist is called Miscellaneous Topics. Look at all the stuff in there. It's all good stuff. But in particular, there's some videos called Drawing 1 and Drawing 2, as I recall. And it's all about everything that I know about how to draw three-dimensional math diagrams, such as for the purpose of understanding triple integrals. So please give that a look if you don't already feel that you're strong with three-dimensional drawing. Okay, so all of that said, what are integrals for? Integrals are for adding stuff up. Any application where the whole is the sum of the parts, right? And so sometimes the whole is distributed over a two-dimensional region. That's where double integrals came in, right? In single variable calculus, we talk about where the whole is distributed over a one-dimensional region. That's what we based it on. And now, sometimes we're adding stuff up over a three-dimensional region. And we just need to tweak the ideas sort of accordingly. So, for example, an easy example, if you want to know how much mass is there in a solid, and of course, again, a solid three-dimensional region, we're going to have to take that solid and chop it up into little pieces. Answer the question for mass on each individual piece, and then add up over the entire three-dimensional solid. Notice also, if mass is distributed three-dimensionally, then density is now mass per unit volume, because that's how we talk about size for a three-dimensional thing. So the good news there is that's the notion of density that we all learned in middle school anyway, right? Mass per unit volume, right? So in some sense, this is an easier notion of density because it's more familiar in that sense. Okay. All right, so let's do it. I'm going to develop a three-dimensional Riemann sum. We're going to end up with this expression down here. I'll sort of talk our way through it. Here's our rectangular three-dimensional box, again starting with a rectangular domain. We get this thing here, and again we're talking about the whole solid on the inside here. And if I want to know the mass on that, or any of a number of other applications, I mean, it's not always mass, right? Maybe this is a fish tank, and there's junk floating around in the fish tank, and I want to know the grand total amount of the little particles of junk, right? If I know what the concentration of junk per unit volume, then again I can chop it up into little pieces and understand the question on each individual little piece, etc. Right? So I'm going to talk through this example with the mass application in mind, just because it's convenient, but very importantly, the expression that we're motivating down here is not peculiar to mass alone. This is for any accumulating quantity. Any quantity where the whole is the sum of the parts. And I'm just going to talk about mass so that I can have something to talk about. Okay, so how do we chop up a three-dimensional solid? Well, we're going to chop in all three different directions. We already know how to chop up the x-axis. We already know how to chop up the y-axis like we did for double integrals. That's all exactly the same. No changes at all to those formulas. We now also, though, have to chop up the z-axis. And that does give us some new formulas, but you'll notice that the structure of these new formulas is just like it was for double integrals. The total height divided by n, and gives us our delta z. Just like the total length divided by n was our delta x. And likewise delta y. So familiar constructions, I hope. And with all of that settled, what I'm going to do with all of that is try to understand one little chunk at a time. So here's a little piece. If you want to compute the grand total amount of mass in here, I'm going to start by asking, okay, well, yeah, but how much mass is there in that one little piece? And as with every other integral that we've defined, double integrals and single variable integrals, the big idea is that density needs to be appropriate to the context. So here, size, the size of this piece is now, it's not length, it's not area, right? This being three-dimensional, this is now a little piece whose size is understood as volume. And so I'll need to take mass per unit volume and multiply by volume. Height, length, width. I guess length, width, height, anyway, volume. Is that cool? Everybody on board? Okay, so mass per unit volume times volume. Or if you're counting, junk floating in a fish tank, junk per unit volume times volume. Oh, if you're computing the population of bacteria in there, then bacteria per unit volume times volume. Whatever the quantity is, stuff per unit volume times volume. Okay, and once you understand how to solve the problem on any individual piece, you add up over all of the pieces, and take a limit to make the round-off errors go away, and we've got ourselves a strategy for how to get a mathematical expression on the question of whatever this application is. Everybody all right? No comment on how to compute it yet. We'll get to that. Okay, so stuff like this that applies so broadly deserves a name and a notation. The name is triple integral. So very importantly, when you hear the phrase triple integral, two things. It is a strategy for how to turn a question about an accumulating quantity into a strategy for how to compute it. Right? It's just this Riemann sum. That's all triple integral means. The notation that we use is pretty believable, I think. This is the notation. Again, though, I emphasize this is just a shorthand, right? It is absolutely not the case that a triple integral is this expression, which is peculiar to one sort of an application, and this Riemann sum is an outdated, useless these days method for computing it. No, not at all. This Riemann sum is what an integral is, and that's just notation. Okay. All right. Okay, so as with double integral, the book goes deeper. Then we're going to go irregular partitions and test points. Very important if you're doing real analysis. That's not what we're doing. We are more interested in applications and problem solving and how to see it and how to visualize it and stuff like that, right? So all these points of rigor relevant to a real analysis class, we're not going to worry about at all. You don't have any responsibility to read that part of the book. Okay, so let's see a quick application. This is something we've already talked through, but how would I use a Riemann sum to get my hands on the question? Get my hands on the question of how to compute a total amount of mass? Okay, well, as we discussed, the whole is the sum of the parts. I like to think of this as a literally translated, the whole is the sum of the parts, right? It just reads straight off of the equation. So that's my first acknowledgement. And then on each individual part, if I have a little piece of mass, how do I compute mass? Mass per unit volume times volume. Right, now this is capitalizing very conveniently on the little integral shorthand that we just discussed above, right? This is using the integral shorthand notation instead of writing out these great big clunky, massive Riemann sum expressions. No need for the clunky, right? And so very convenient to write it like this. How we doing? Everybody with me? All right. How do you visualize triple integrals? This is a tricky business, frankly. And the biggest problem, as I see it, with how to visualize triple integrals is the bad choices that most students have been funneled into in how they visualize earlier kinds of integrals. So let's talk about these points of view right here, and you'll recall that I've been kind of cool on the idea that you should understand integrals in terms of graphs, right? Should you understand a single variable integral as area under a graph? You can, but it's really not the point, right? And likewise, analogously, should you view double integrals as being volume under a graph surface? Well, you can, but it's not really the point, right? And I'll remind you, in actual real-world situations, it's actually quite rare to need to compute area under a curve. It comes up as a visualization tool for computing something else, right? We draw graphs and talk about the area under a curve if we're interested in computing work or probability or any of a number of other accumulating quantities. Sure, but the area is not the point most of the time, right? So I think it's kind of a weird way to represent something when it's geometrically different from most of the things it's supposedly representing. I am much more of a fan of understanding single variable integrals, what you might call one-dimensional integrals, in terms of a one-dimensional application, thus giving me a one-dimensional picture to go along with my one-dimensional integral. I think this is really more natural. In fact, think about it, that's what an integral is. An integral is trying to address a problem where stuff is distributed over a one-dimensional interval. That's why they call it single variable integrals, right? So one-dimensional integral, one-dimensional application, one-dimensional picture. Everything fits. Likewise, with double integrals, that's an intrinsically two-dimensional thing. It applies mostly when stuff is distributed over two-dimensional domains. I think it makes sense to understand it with a two-dimensional picture. just, again, everything fits that way. Okay. All right. So here's the problem then, right? So moving along to our new situation, we now have to figure out how to understand triple integrals. Well, if you're really all in on understanding one-dimensional integrals with a two-dimensional picture and two-dimensional integrals with a three-dimensional picture, you could probably see this coming. You're going to sort of be trying to visualize a three-dimensional integral with a four-dimensional picture, and that's a loser. You can't do that. It's just not. I mean, we're stuck unavoidably in this three-dimensional universe. We are, sadly, merely three-dimensional math students, and we can't visualize four dimensions. So this is one of my big complaints. You know, one of the reasons why I don't really want to think about integrals in terms of graphs is because it sets up an unsustainable pattern that leaves you out in the cold with no tool for visualizing triple integrals. Okay, so the solution to this problem, no big deal, really, is you just need to rewind and reacclimate yourself to how to understand these integrals that we've talked about in the past with dimensionally appropriate pictures. Right? Take the time as is necessary to, kind of acclimate yourself to thinking about single variable integrals in terms of stuff accumulating over a single dimensional interval, like mass of a rod, for example. It's easy. My favorite sort of most relatable example of this. So my favorite metaphor for single variable integrals. And likewise, try to reacclimate yourself to thinking about double integrals as, how would I compute the amount of mass distributed over a two-dimensional region? The dimensions all fit. Right, you want to understand a one-dimensional integral, you get a one-dimensional picture. Two-dimensional integral, two-dimensional picture. And then when you want to extend to, now how do I understand a three-dimensional integral? No problem. Three-dimensional picture, it's all good. Everybody on board? Okay. Last little super quick word of warning. I know that this is a tall order. Right? And you may be pretty heavy in on this point of view of single variable integrals, and I've been warning against this point of view on double integrals, but I understand that because of the pattern, a lot of students really like to cling to this one as well. If you insist on thinking about single variable integrals this way, double integrals that way, and then for lack of better options, thinking about triple integrals this way, you're going to notice pretty quickly that mysteriously sometimes a three-dimensional picture is a double integral and sometimes it's a triple integral. And how do you know when's it a double integral, when's it a triple integral? It is legitimately confusing because you are pretty directly making apples and oranges comparisons between pictures. So again, if you insist on sticking with those points of view, this is something you're going to have to deal with. So that's why I don't like that myself. My primary point of view on integrals for the last many decades is all of this right here. I think it's the best way to think about it. Pausing for questions. Everybody all right? Okay. So, y'all will recognize this diagram, or at least the structure of this diagram. This is new, of course, but we have already made this connection here that applications can be addressed by Riemann sums, chop it up, add it up, whole is the sum of the parts, Riemann sums. So that we know. We've seen an example of that already. I think it's a pretty easy sell that if I were to write a triple iterated integral, that is an integral inside of an integral inside of another integral, Well, those are, in fact, still single variable integrals, and you can just crank them out one at a time. There's going to be 3 of them instead of 2 of them, but it's still single variable calculus. It's just fundamental theorem of calculus 3 times in a row. So I hope this is believable that is going to be easy. So here we find ourselves again needing to know, is there a relationship between triple integrals and iterated integrals? And you may recall that at this moment in our development of double integrals, there was this 3-dimensional idea of volume that we could cleverly compute a couple of different ways and draw a conclusion, and that worked really great. But now, sadly, this is a 4-dimensional problem now, as previously discussed. So I can't make this argument, not because it wouldn't make sense, but because it only makes sense in 4 dimensions, and we're not that kind of critters, right? And likewise, I can't make that argument either, not because it doesn't work, it's because it's not something we can personally relate to. So I'm going to assert that it actually makes perfect sense. It is fine, and yes, indeed, triple integrals can be written as iterated integrals. It's just harder to see it geometrically. Now, how do I know? Am I claiming that there's some 4-dimensional argument that we're not going to do? No, not at all. There is a different way to say this conclusion. It is algebraic and subtle and sophisticated and formal and not really what we're interested in this class, right? So rather than try to make some sort of a case for why these are the same, I'm just going to assert and suggest that the best way to deal with this is for you to just trust me, if you would, that in fact, yes, triple integrals can be rewritten as triple iterated integrals. And this is the result. This triple integral can be written as any of these iterated integrals right there. Okay, so just like with double integrals, we can't relate the application directly to 4-dimensional nonsense that we can't even understand in the first place. And just like with double integrals, we also can't just go straight to iterated integrals because the units don't work out in the individual integrals on the inside. So with the understanding that those are non-starters, how do we get from a question to an answer? It's the same 3-step process. All the same comments apply that, yes, you do have to show me the triple integral, because that's the very non-trivial, important construction that allows for connecting to applications in the first place, and you have to rewrite that then as an iterated integral, because that's the only thing that we know how to compute, right? So we have the same scenario where we're going to have to see 3 separate steps, and please do make sure to, at least, however briefly, give me all 3 of the steps. Okay, is everybody on board with all that? Okay. All right, so here's an example. All 3 steps. The question is to compute the amount of mass in a rectangular box. We already kind of did the first part of this. We already know that mass is a triple integral of density. We argued that near the very start of the class. Top of the second page, as I recall. The theorem above tells us that the double integral is the corresponding iterated integral. Now let's think about this carefully. Our rectangular box, you'll notice, here it is, our rectangular box. I'm using this notation. We've seen an analogous form of this notation with 2-dimensional rectangles. This is exactly the analogous thing. This is the range of values for x. This is the range of values for y. This is the range of values for z, defining the box. And so when you start with your integrals, let's see here. You want to know the range of values for your y integral with y on the outside. Arbitrarily, I'm putting y on the outside, not that it matters. Well, here's the range of values for y, so those are your y bounds. Next, for no particular reason, with x as our next inside integral. Okay, well, this is the range of values for x, and so those are my x bounds. And then likewise, proceeding, what's the range of values for z? Well, 0 to 1, and so that's my z bounds. So that's how you turn a triple integral over a box into a triple iterated integral on the box. Just a matter of looking at the given ranges of values. What do you think? Everybody good? All right, and then the last bit is very plug and chug, so I'm going to mostly let y'all read that. I will call your attention to a couple of things. This inside integral, of course, you have to integrate inside out, starting at the inside. That inside integral, in the process of doing that, notice that our variable, z, that's the actual variable. X and y are constants, so z is the thing that we're plugging in these numbers over here for. So notice I explicitly write z equals, so that I don't lose track, because it's surprisingly easy if you don't put that little cheat in there, right? If you don't remind yourself, it's surprisingly easy to plug the 0 and the 1 in for x's, or something like that. Okay, so I advise that. Yes?
How come there's a soft bracket in the front and a hard bracket?
Oh, yeah, that's just kind of a aesthetics, really. I mean, so this, right bracket like this, the square bracket means you're going to take these values and plug them in and subtract. That's just, again, a nice little shorthand. And I just put this here so that it wouldn't look like, I don't know, it's just to separate it from the x integral. That's all. Yeah, doesn't mean anything. Yeah. So the other thing to keep in mind is that while you're doing the inside integral, don't forget that the variables further to the outside are to be treated as constants, because, as we will see on the next page, they really are. And so in particular, x and y being constants here, notice they just kind of come along for the ride as multiplicative constants do. And the actual variable being z, it's just the sort of the 2z whose antiderivative is z squared that I have to actually do anything with. Or if you prefer, you can think of 2 as a constant, and then you get a 1/2 z squared, whatever. The point is x and y are to be treated as constants. Okay, all the rest is details. That said, therein lies the devil. Right? That's the old expression. So make sure you're good with this. Right? I can sort of wave my hands at it, yada, 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 but y'all are the ones who are going to be taking a test where you're actually going to have to crank all that out. So I think it's a really good idea to not only make sure that you follow the details that I've got in here, but make sure that you can reproduce the details correspondingly. Right? And so you might, for example, take this, write this on a clean sheet of paper, right? Don't look at the stuff down here. And then on your clean sheet of paper, force yourself to make your way all the way through there and make sure you get the right answer. Okay. Non-rectangular domains. Notice how we're going through all of this sort of preliminary stuff very, very quickly by comparison to double integrals. We're going to rip off the method that we did for double integrals. Let me remind you how that worked. For double integrals, non-rectangular domains, this is one of few instances where I do think it's very convenient to think of the double integral as computing a volume, because it gives us something that we can kind of look at and get our hands on. And recall that we first slice in one direction arbitrarily. I'm going to go in the y direction here first. Right? So y integration on the outside. And then for the inside integral, this whole inside integral really is just an attempt to compute this cross-sectional area. And so the integral in the x direction represents that cross-sectional area. Right? Now, we didn't visualize things this way in practice because this is a harder picture than necessary. But notice all that's happening is I'm slicing in one direction, keeping track of starting and ending values, and then looking at the corresponding slice, looking at a corresponding fixed value of y, and then slicing in the other direction. So we start by slicing in the y direction. We get these y slices. To understand the y slices, we have to further slice in the x direction. Okay, so we're going to rip off that general strategy. Again, I claim that this works, and the corresponding picture is four-dimensional, and I can't really, we can't see that. But same process. Decide what direction you're going to slice. Find your bounds based on where the first and last slices are. Fix a slice and repeat. You go back and you do it all over again with your next variable. Okay, so let's see this in action. I've got a picture drawn here. Reminder, you can kind of do this in any order. There's 6 different ways that you can order your differentials. So there's 6 different geometric versions of how to slice up your solid based on these 6 different possible orderings of these differentials. We'll talk later, probably not today, but on Friday we'll spend a bunch of time doing, again, lots of examples. We'll talk about the pros and cons and considerations of which order should you slice. So for the moment, until then, I'm going to arbitrarily pick one, no particular reason. We're going to start with x slices, and here we go. X goes from there to there. Our x slices are going to be something like that for this lump of a three-dimensional solid that I'm working with here, right? I can see where my first and last slices are going to come from, right? Slices like this that are perpendicular to the x-axis. The very first one is going to be that farthest back point back there, the tippity very back, farthest into the screen point, and that's going to give rise to my lower bound for x, and then the last slice will be this closest point right there on my lump, and that gives me my ending value for x. And so with those identified, x1 and x2 are my x bounds. Cool. Okay, following the pattern, we now fix a value of x. All of our attention for the whole rest of the question is focused on, I'm going to say, one slice at a time. Now, again, this does weird some students out. Wait a minute, we're only going to look at that one slice? Am I not interested in that little piece of the domain over there? Well, yeah, of course I am. And that is part of one of these slices. That's part of a different slice. That point there is part of, this slice for, let's say, that value of x. So, yeah, we'll get to that point, sure, for other values of x. But we need to know how y and z vary with x, as a function of x. And so that's why we're going to be restricting our attention just to arbitrary x slices. And then, of course, as x ranges over all of its allowed values, it will sweep out the entire solid. Okay. All right. So, again, x fixed. Looking at this x slice. Moving on to the next geometric step of y slicing. Well, y slices are kind of like that, right? So I have this pre-existing x slice that's kind of oriented like my left hand here, and now my y slices are going to cut through that x slice, right? And the y slice of the x slice is just that little line segment right there. That's what y slices look like. And now let's talk about starts and ends. Well, the first one of these y slices is just that point right there, which gives me my y1. Notice it depends on x. For different x's, right, as I consider different values of x, I get entirely different cross sections, which will have entirely different y1. So the y1s are functions of x. Notice the pattern from double integrals continues. The bounds on the inside integral are functions of the outside variable. Alrighty, and then likewise, the last y slice is there, giving me my y2, which is also a function of x. And so my y bounds, y1 of x and y2 of x. Now, geometrically, how are we doing here? Well, algebra to follow in the explicit examples we're going to do in just a minute. Everybody see the strategy? No? Okay. All right. And there's a third step. Again, 3 dimensions instead of 2. 3 integrals instead of 2. Always 3 instead of 2. So looking now at x being fixed, still x being fixed. And now let's take y also fixed. Looking then just at this y slice of our x slice. We are now interested in the range of values of z. And z starts at that point, thus has that lower bound. And z will end at that point, and thus have that upper bound. And there you go. Notice we now have our triple iterated integral. Right? An integral with an integral inside of it, inside of which is another integral. Is that cool? All right. Just following the pattern from double integrals. Okay, so I think I've already commented on these various notes here for this inside integral. Notice general rule, whichever variables are further to the outside, those variables are to be viewed as constants within the inside integral. Again, why? Well, because if you look geometrically, they literally are. For this z integral, we're looking only at those points, and at those points, x and y are all the same. So they are literally constant, thus treated as constants. Okay. All right. Okay. So yeah, when it comes time to actually compute these great big monstrous triple iterated integrals, you are going to have to compute outside to inside, right? I can't even begin to think about doing the dx integral. I haven't worked out yet what the integrand is for the dx integral. The only integral in this picture whose integrand I know is the inside integral, the dz integral. Whatever your f is, whatever your mass per unit volume is, whatever your quantity per unit volume is, whatever the quantity, doesn't matter, right? That's what's given and known, and so the dz integral I can actually crank out. And once I know that, then I know my integrand for my dy integral. And once I crank that out, then I finally know my integrand for my dx integral. So always inside to outside. Always outside. It's inside to outside. Sorry, I misread my own notes here. We construct the integral outside to inside. We compute the integral inside to outside. So I misspoke there. I'm sorry. Does that make sense to everybody? Did I confuse anybody there with my... And as we've done with double integrals, if you want to understand what a bound is, it's going to come from a corresponding point. That point you will identify as being on certain geometric objects, in this case surfaces, and those surfaces will have certain equations in which you can solve for the point, for the bound. Okay. All right, so example. Okay. What I want to focus on with this example is not the answer. Certain aspects of this problem, you could probably kind of figure out without actually following the specific mechanical process that I claim will always give us what we need. So the process is what we want to focus on here. If at certain points you feel that you could kind of outsmart the process in some way, don't. Because again, it's not the result that we're interested in, it's the process itself. And when harder examples come around, you won't be able to kind of look at it and see. And in those cases, the process is the thing that will save you and will actually allow you to solve the problem. Okay, so let's focus on that. We have a tetrahedron, sort of a three-dimensional version of a triangle, kind of, sort of, right? And various planes defining it. And this is going to be our domain for a triple integral. Why are we interested in this triple integral? Not the point of this exercise. I'm going to assume that the phase one part of the problem is done for us. In other words, maybe F is mass per unit volume, and therefore this is mass. Or perhaps maybe F is population per unit volume, in which case this is population, whatever. Any of a number of applications. Let's not worry about where this came from. Given that I have a triple integral, our question is going to be how to turn that into an iterated integral. Again, arbitrarily, I'm going to do my slicing in this order. No particularly good reason. You have 6 total options. In this case, it really wouldn't matter which of those 6 options you pick. I'm picking one out of a hat just to get a foot in the door. Okay, so here we go. X slicing. And you can see what our X slices look like. I claim the first one is like this over here. Then there's more as you proceed along, and the last one is there at that point there. So here's our first and last slices. We need to understand what the corresponding values of X are, because we want to understand the bounds on the X integral. So let's take them one at a time. The first one really is easy. If I want to know what's the value of X on that back face, that entire back face is evidently from the picture in the YZ plane, which has equation X equals 0. So it's pretty much a freebie that our lower bound for the X integral is X equals 0. So sometimes it really is easy. But things get different when you're looking at the upper bound for X. Now, how are we going to understand that upper bound for X? And here's where you need to rely on the method. And again, I understand, yes, I recognize that you can take these equations and you can do some geometry in advance. You kind of know where everything is, and maybe you feel like it's geometrically obvious that this is a 1, right? Not the point. We're interested in the process. What is the process by which I can conclude that that's 1? And here it is. I can tell from the picture, thank you, picture, that point that defines my last slice is on this plane, the plane y equals 0. I can also see from the picture that the point I'm interested in here is also on that plane. That's the plane z equals 0. And I can also see from the picture, got to have a picture to see this, that the point I'm interested in is on that plane. So altogether, if I want to know about that point, if I want to know where is that point, and more to the point, where it is the value of x for that point, well, then I need to solve this algebra for x. And you get x equals 1, and thus our upper bound for the x integral is 1. So this is the process. Identify the relevant point. Identify that relevant point as being on what geometric objects that have what equations. And then with all of those equations, describing all of the geometric objects that contain the point that I'm interested in, then it's just a matter of doing the algebra, solving for the variable that you need, and that is your bound. And it looks like I am out of time. So we will pick up here on Friday. Thank you. Yeah, all right. See y'all later. Have a good one. If you didn't get marked down for attendance, make sure to talk to me. 2 seconds.